lesson 2, transformations. So we're going to continue with the other transformation types that we started last class. So last class, we discussed 2 types of transformation. We did translations, so movements of the graphs left, right. Okay, those are called translations, or sometimes shifts. We don't use the word shift because now that we get to stretches, we don't want to use S for 2 different transformations, and then we get confused which one is which. Okay, so we use the word translation. And then we got to practice also with reflections. So we had vertical reflections that changes the Y sign coordinate. And we also looked at horizontal reflections, which changes the X coordinate of your points to a different sign. And these ones are translations. I only did the horizontal ones, but we also did movements up, down. Do you have any questions about last class in terms of translations and reflections?
I had a question. It was, just let me find it here. On 1.3, on the third question B, the answer, I just wanted to ask a little question if it needed to be an improper fraction in our answer, or if you could write it as like the whole number and then I guess the remaining of the fraction behind it, or if you wanted it as the full improper fraction.
So I don't mind if it's superimposed fractions, or if you write it as a mixed fraction, or if you write it as a decimal, because all of these forms are equivalent to one another. The only problem with fractions when you're converting them into a decimal, and then you have to round. So unless you don't, since you have an exact number with all of those forms, you can do either or. If you have a fraction, for example, 1/3, and you want to write it as 0.3, okay, that's no good, okay? So if you have 1/3, you keep it as 1/3 because this is better than 0.3, which is already a rounded version, okay? But if you have 1/4 and you write it as 0.25, that's
that works.
Okay. If you have 4/3, or if you write it as 1 1/3, that's correct to both of these forms. Okay.
Yeah, I was just asking because I feel like it would be easier to plot points on a graph if you had to graph using this like form.
Yeah, this one is easier. Decimal easier. If you're doing it for graphing purposes, you can always calculate it on the side, right? Because you need an approximation to know where to graph. But yes.
Right. Okay.
Okay. Any other questions? Okay, then we're gonna get going. So let's talk about the vertical stretches and compressions. I have here the first type, the g of x equals 2 times square root of x is going to be our example we're going to use to discuss the vertical stretches and compressions. And we notice that 2 sits in the same place that we have talked about vertical reflections, where we had our negative or -1 in front of our functions. So when we have a number in front of our function, think about the square root of x being the f of x function, okay? One parent function of any kind of type, even a given graph. When you have a number that's bigger than 1, that's going to be bigger, making all of your y coordinates larger than they were before, right? So 2 times whatever it was before is going to be twice as large as it was before. So that's going to stretch the graph vertically, or in the vertical direction, by a factor of whatever the number is, in this case 2. So now last class I've shown you quite a bit of work with with a table of values, and we can continue to do a similar approach if it's needed, but I think you can already see the pattern that the graphs are taking based on this equation that we call the standard form equation. So they all started with table of values, and you analyze the relationships. What happens if I keep the variable x in one spot? How can I connect the y variables? And then we just plug it into an equation that would match for these changes. So we're going to move a little bit away from that today, and we're going to just plot straight what this means. Okay, so we know that square root of x is our parent function with the points 0, 0, 1, 1, 4, 2. That's our square root of x function. And because this is the vertical transformation, for these types of transformations, your x variables are staying in the same value, the same spot. So in this situation, if you want to always not make a mistake, keep a ruler on top of your graph points and keep it vertically because we're doing a vertical transformation. And then you're going to multiply by the factor you had in the position of A in this case. So this is 2. We call this a vertical stretch by a factor of 2. Vertical deals with y, so 2 times y. So we're going to go here to our graph. 0 is the y coordinate of this point. So 0 times 2 equals 2. So this point doesn't move. We call sometimes these points invariable, doesn't vary. The next point, the y coordinate of this point is 1. So if I times it by 2, I'm going to get to 2. What's the x coordinate of this point?
1.
1. So it doesn't change, right? That's why it almost looks like we do a translation, a movement of the graph, but we don't. We're stretching the y values of each of the points. And even these points are stretching, the ones that we're bypassing, but we're only going to use some key points because they're a little bit nicer to work with. When we get to our third point, the point 4, 2, we work with the y coordinate 2. So 2 times 2 is going to be 4. Again, the x stays at 4. Now we have our 3 points, the one that hasn't moved, the one at 1, 2, the one at 4, 4, and we're just going to do our swoosh through those points. So that's the graph of the stretch function to square root of x. Okay, so let's have a look at the function at the bottom of this page. Now we're going to graph it on the same page here. We have h of x equals 1/2 of square root of x. When you're multiplying the function, which is f of x, sometimes we call it, or even y, you can call it, because not all the time we name it with the function notation. So when we're multiplying our y values now by any number that's in between 0 and 1, and we don't want to think about negatives in this situation and also in the stretch situation because we deal already with the negatives as reflections, so separately from reflections, just the actual number. So if that number is somewhere between 0 and 1, a decimal, a fraction, it doesn't matter. As long as it's less than 1, now you're going to reduce the value of the original y by that factor. So we're just going to call it a vertical compression by a factor of whatever the number is, in this case, 1/2. So it cuts it in half. Since it's the same transformation, just not a stretch, but a compression, the method is the same. We're just going to keep our ruler vertically, take point by point, and only deal with the y coordinates. So this one is 0, 0 times 1/2, it's still going to be 0, so stays there. The next point on the original parent function square root of x is the point 1, 1 with the y coordinate y. That coordinate is going to be reduced now into half because 1 times 1/2 is 1/2. The next one has a y coordinate at 2. 2 times 1/2 is 1, or 2 divided by 2 is 1. There are our 3 points. And there's our sketch of the graph of 1/2 square root of x. Now, visually, when you look at a vertical stretch, you can imagine that the graph is going to go a little bit steeper than before because you're stretching it in the vertical direction. If you're looking for a vertical compression analysis, your graph has to be now closer to the x-axis because you're pressing it down in the vertical direction. Each of the points of the new graphs, the image points we call them, they can be described by this relationship. So an original point xy becomes a new point x, comma, so x stays the same, a times y. Where does this a come from? Turn the light on here. Does anybody know where the a comes from?
From the top.
That's right, from the top. That sounds like a new voice. There's a few pieces here. Okay, and Greg is here. Welcome. So yes, from the top, this expression or equation, it's called the standard form equation, the one that we use for reading transformations. So when this a is a number that's different than 1, and also it can be negative as well, but the negatives, again, we've talked about last class as being reflection. So if it's different than 1 except negatives, that's going to give you either a vertical stretch or a compression. But the method is going to be the same, including for points. You just take that number and you times it by y, keeping all the x coordinates the same. Any questions for vertical stretches and compressions? Move on to the first page of examples here. We do a couple of these examples and we go to the next part, which is horizontal stretches and compressions. The graph of, oh, they have the same one here. Let's change it to a different function. Let me see what I gave you. 3x squared absolute value in there, but 2/5 here. Okay, so let's do the cubic one. Sketch the graph of 2x cubed, state the domain and the range. So for each of these transformations questions, when you have to graph, the steps in the way you're going to have to show your work are always going to be the same. So you have to state somewhere what is your parent function. So parent function is our cubic function. And then make sure you include the graph of this parent function. So we're going to go for the graph 0, 0, 1, 1, 2, 8, and then in the negative direction as well. And then you want to make sure that your equation is written in standard form. So when it is in standard form, you want to make sure that in front of x, underneath the type of function, everything is factored out, okay? Because then if you don't, you're gonna affect the horizontal translations. This one doesn't have a horizontal transformation there in front or after, so it's good to go. So for this one, it doesn't really matter if this 3 is inside or outside, but in the end, this 3 has to come outside to show the same notation as we use for standard form. We're focusing on vertical stretches and compression, so the only number we have to work with is 2 here in front. This 2 is a number that's bigger than 1, so it's going to give me a vertical stretch by a factor of 2. So 2 times 1. And we label all transformations in the description and in the graphing. So we go here. Usually I graph my graphs, the final ones, in red, but since I use green here, I want to continue with green. So again, we're still learning about these ones. So vertical transformations, you can keep your ruler vertical. Remember, you only have to deal with the y coordinates of each of the points for all the vertical transformations. Let's start at 0. 0 times 2, just like with the example in the notes, stays there because 0 times 2 is still 0. Then you go to this one. 0 times 2 is going to be, oh, this is not 0, this is 1. 1 times 2 is 2. So we put it at 2. And the next one is going to give us trouble, right? Because it's going to be 16, right? So we don't want to do anything further down. This is enough to show the stretch. And then you go to this point over here, and you have it at -1 for your y coordinate. -1 times 2 is -2. And you have another support point. And again, you know that if you take this point here with the y -8 times that by 2, you're going to get somewhere to -16. So you know how to graph it towards that next point, even though you don't see it. And then we're just going to unite the points and show that vertical stretch. And then we label it. The min and range for all cubic functions always going to be the same. X belongs to the real number, Y belongs to the real numbers.
So if our point in our equation goes off the chart, you don't want us to do like that little squiggly line and extend the graph or anything like that.
No, not necessarily, unless you need that extra support point to kind of complete the visual of the graph, but this is very simple shape. So as long as you see that shape of the graph, you don't need all of the points.
Okay.
Yeah. So that was number 1. Number 2, sketch the graph of 2/5 of absolute value of x, domain and range at the end. The parent function is absolute value function. And then here, I'm going to be a little bit clever about the choice of my points. With the vertex, I don't have a choice, 0, 0. But because I see that the number in front of my function, the one that's going to dictate if it's a compression in the vertical direction or a stretch, is a fraction over 5, right? So because I'm going to work with a fraction over 5, I'm going to choose my next set of points as multiples of 5. And you'll see how easy that would become. So 5, 5 on this end, and then 5, 5 on the negative. And then I do my sketch. I don't know if you remember when we first did these graphs, the absolute value graphs, I told you these 3 points are not going to be always the same. It's going to be dependent on your needs. So here's the first example where we actually can choose depending on our needs. So 2 over 5, is this a number bigger than 1 or less than 1?
Less.
the best, right? So since it's less than 1 and we multiply our y by a number less than 1, they're going to be reduced. So we describe this as a vertical compression by a factor of 2/5. That's going to be our only graph. So 0, 0 doesn't move. This first point, the y coordinate is as 5. So 2/5 times 5 will be what? 2/5 times 5, cancel out, equals 2. And that's why I chose the point with 5, multiples of 5. So right there, at 2. Same thing on the other side because this graph is symmetrical. Right. And done. Domain and range. Domain is all of the real numbers. So it stretches left, right, to infinities. And then for the range, all of my red graph is above the x-axis. So y is bigger and equal to 0. You can try these a little bit later, the your turn number 1 for today. We're going to move on to example 3, working with some points. So we have the point -2, -6 that belongs to the function f. And we are to find the new point that is going to be shown into a vertical stretch because we have a factor here of 3 in front. Then we're going to have a vertical compression of 1/3. We're going to see how that looks in the image point. And then we have a combination of all of the transformations we've learned so far. And we're going to look at how that point will take upon all of these transformations. So let's get started with the 3 times f of x, and that is a vertical stretch by a factor of 3. And we already know what to do to our point. So the point -2, -6 belongs. -2 stays. We have to take our y coordinate and times it by 3, right? So 3 times -6. Point will become 2 and -18. Negative. I forgot my 2 along the way. This is a vertical compression by a factor of 1/3. Again, it tells you exactly what to do once you understand and you memorize what you have to do for the transformation. All you gotta do now is apply it on the point. -2, -6, vertical transformation doesn't affect our x coordinates, so -2 stays, and all you gotta do is times our y by the factor 1/3. And the point is -2, 3, and 6 can cancel by a factor of 3. We get -2. Any questions for A and B?
How did you get the VSVC?
And VS means vertical stretch. So based on our previous examples and notes, we know that when the number is bigger than 1, the graph will stretch. So we're going to call it a vertical stretch. When the number in front is less than 1, between 0 and 1, particularly, then the graph will compress vertically. So we're going to call it a vertical compression. So just the name of this transformation. Any other questions? Okay, so in C, we're gonna put it all together, all of the transformations we have done so far, and we have to be careful which ones are horizontal and which ones are vertical. So let's rewrite this function. So 1/6 in front, f of negative x plus 2 minus 4. For the vertical transformations, those values are usually direct, okay? So they won't really change anything. You don't have to be careful in writing your equation too much in standard form. Sometimes this negative 4 might be written here before the equal, so it might appear as y plus 4, and then you just have to move it on the other side, okay? But that's pretty much all that can happen. But for inside of the function where the horizontal transformations live, you always have to be careful if there's something in front of your x, because if there is, you have to factor it out before you can read the transformations. So that's our first step. Make sure we write our equation in standard form by attacking this factoring right here. So what's this number that we have to factor in front of x?
Negative
Negative is not a number, so what is the number?
1.
Negative 1, that's right. So negative 1 in front, bracket, we're left with x minus 2. Now it's written in standard form. Here I can just put plus minus 4, but it's not necessary. We can just read it as it is. Okay, so now let's go from left to right and describe the transformations. This one here is our a parameter 1/6. The one that sits in front of the function, it's 1/6 times. That's going to give you a vertical, either stretch or compression. So when you're multiplying by 1/6, your y coordinate, what's going to happen with that value of your y coordinate, the one from before? Is it going to be larger or smaller?
Smaller.
Smaller. So therefore, this one is called a compression or stretch?
It's a compression.
The compression. Okay. Good job. Now we're going into the inside part to discuss our horizontal transformations. Now, this is our b value in the standard form. This b value, we haven't really talked about being an actual number that's different than 1 or negative 1, but we did talk about it being negative. So what happened when the b value was negative from last class?
Makes our x value like change sign.
That's right. So x will change sign. And when that happens, when you have a graph, when you change the x from negatives to positives, or from positives to the negative side of the graph, what's this movement of a graph?
The reflection.
Reflection. So that's called the horizontal reflection. And now we get to this 2 here that sits where we call the c parameter is in the standard form equation. And that's the first type that we talked about last class, not last class, I think 2 classes ago, the translation. And we have to remember to pay attention to this one because we read it oppositely, okay, all the time for the movement of the graph. So it is a horizontal translation 2 units where? Right or left? You always go with the opposite of your intuition, based on what you see here,
To the right.
to the right. So x plus 2 will move your graph to the right. That's what you have to do to the x coordinate of your points. And I'm going to keep my labeling, the color labeling the same. I'm going to keep the y's in green. So I'm going to go back to this -4. And that's a vertical translation, so movement of the graph in the vertical direction, up or down 4 units.
It's down because it's negative.
That's right. So this one goes as is, this one always opposite of what you see. So y -4. Now all we have to do is apply these rules, but consecutively onto the point that we have. I always like to design myself a little bit of a rule to work with. So the point xy on the original function, which is our point -2, -6, will become the point, and then you take the x, this -x, and you plug it in here. So you replace that, becomes -x plus 2, comma. And now for the y, you take this transformation and you plug it into the next one. Replace this y. So 1/6 y -4. There's your rule. Now let's apply the rule onto the point. The point is -2, -6. Let's see what happens. We have a negative, and then we plug in -2 there, and then we have to do +2 to it. And then for the y, we have a 1/6 in front of it. We plug in -6 and -4. Negative and a negative makes a positive, and that means 2 plus 2 equals 4. The 6 and the 6 cancels out. We're left with -1 -4 is -5. 4, -5. Everybody got the notes? Any questions?
Can you hold on just one more minute for me to write it down?
For sure.
All right, I'm good.
Okay, everybody else good? Okay, horizontal compressions and horizontal stretches. So we're going to use again the square root of x. That's our parent graph. I hope this is big enough for us to be able to see it. So let's do 0, 0, 1, 1, 4, and 2 right there. So we are going to look at the graph of square root of x again to see how it's going to look like for horizontal compression and stretches. So where will be the number that's going to dictate if we have a horizontal compression or a stretch? Well, it's going to sit under the function. So if I replace this notation with the notation of f of x, so if I say let f of x be square root of x, this will look like that. F of 2 x. With or without bracket, it doesn't matter, okay? So it's inside the f of, underneath the type of function, okay? If you have squaring or cubic functions, it will be under the squaring, so you'll see the 2 right here, again with the x. If it's cubic, you'll still see it over there. So that's where it is, and this parameter is called the B parameter. We've seen it for horizontal reflections, but we only seen it as a negative. What happens if that position is only a negative number? Now we see it as 2 here, right? Now the intuition would tell us, oh yeah, I just times it by 2, all of the x coordinate, but that's not what happens, okay? It's gonna be actually the reciprocal of 2, the opposite way it was for the vertical stretches and compression. So if this number is bigger than 1, you actually will have a horizontal compression by a factor of what we call the reciprocal of this number. So 1 over 2 times x. And hopefully if we have time, next time we're in class, we actually can look at the table of values and we see how that looks like, because yes, indeed, it's going to be shown on a table of values as well. Okay, so the reciprocal of 2 is 1/2 because the reciprocal comes from inverting the fraction form of a number. Or when we say 2, we can write it as 2 over 1. So just flip it over to get the reciprocal. So 1 over 2 would be the reciprocal. Okay, so now we know what we have to multiply our x coordinates by 1/2, or just cut them in half. We're doing a horizontal transformation, so your ruler has to be horizontally situated. So 0 is our x coordinate here, so 0 times 1/2 is 0. The next one, our x coordinates, so make sure you carefully looking at your x's, not your y's. Okay, so x is this one. We times it by 1/2, we're gonna get here. And then we go to our next one. Your y stays the same, your x's will change. X is at 4, times it by 1/2, we're gonna be at 2. That's the graph of 1/2 of x. Let's put the square root, not 1/2. 2 times x square root. That's what we did to it, 1/2 of. So now, visually, why is this called a horizontal compression, right? Because if you imagine pressing now the original graph horizontally, the graph has to now be steeper, right? Or narrower. Now, how are we going to look like stretches? Well, if we notice that the numbers are larger than 1, gives us now horizontal compression. Obviously, the numbers are going to be less than 1 underneath the function in front of x, where the b variable is. That's those numbers will give us stretches. Now, what is going to be the factor by which you're going to stretch? You're going to have to find the reciprocal of this number. The reciprocal of 1/2 is 2 over 1, or just 2, and that's what you're going to multiply your x variable by. And that's called a horizontal stretch, because if you stretch your x's by 2, you're going to get larger x's that you had before. Now, let's go to our graph. Again, a ruler is horizontally situated. 0, 0 doesn't change. 1 times 2 is 2. So we're going to mark it there. And then again, 4 here is the x times 2 is going to be somewhere at 8 there. If it's going out and you still see the shape of the graph, you don't have to long as we can see 1 or 2 points that you transformed. And that's the graph of 1/2 x under the square root. Here are your notes. There's your b variable. Notice how it's factored out, always factored out. And if you want a rule of how to get to that reciprocal, you can just take your x and divide it by the b, which is here. Your x will be divided by 2. It means the same way as if you multiply it by 1/2. Notice the absolute value. That's just ignoring the number being negative, because we want to treat the negative separately as reflections in the horizontal direction for this one. And then to sketch the graph, you just have to get this multiplier value. So you always have to be careful. Don't just take the 2 times the x here. You have to first reciprocate the values and then times them by the x coordinates. So let's do some 2 examples here with the graphs. Again, the same pattern for showing your work for everything that involves graphing. So first thing, we have to identify the parent function. And here we have y equals 3x everything squared. So it's a squared function. So the parent is x squared. That's a parabola, 0, 0, 1, 1, 2, 4, and then the other side exactly the same because it's symmetric. Y equal. Now 3 is in front of the x underneath the function. Even though in this case it doesn't matter, I want you to get in the habit to always separate it from the x. And then you just watch to see what happens when you do that factor. In the situation, there's nothing else that's going to affect it. Okay, so nothing will happen because of your factoring. But if you always do it all the time because you know the rule, then you won't make a mistake when you actually need to separate it. Now, okay, we know it's underneath, so it belongs to horizontal direction. That means we're going to have a horizontal something, okay? I always stop here because I want to decide if it's compression or stretch based on the reciprocal of number 3. The reciprocal of number 3 is going to be 1/3, right? So 1/3 times x will make my x smaller than before. That's going to be a horizontal compression by a factor of 1/3. And let's have a look at this graph. We color it in pink because I'm going to use pink for this one. So horizontal direction, the ruler is horizontally situated. The vertex won't move because we have the 0 for x. 0 times 1/3 is 0. But these 2 points will, because 1 is the x coordinate here times 1/3. So just eyeball it where 1/3 is. And then for 2, we need 2/3. 2 times 1/3 is 2/3, so somewhere there, and then negative 2/3 somewhere there. The graph has to look visibly narrower because we compressed it horizontally. So imagine compressing. domain all the real numbers for the red graph and y bigger and equal to 0. So nothing really changed for domain and range, just by doing a stretch or a compression in the horizontal direction for this function. Absolute value of 1/3 of x. One-third bracket x. So always separated. Why? Well, because it's underneath these absolute value lines, so that's inside of the function. So that's our b parameter. Now, I know it's going to be horizontal transformation. I just have to decide if it's a stretch or compression. So I do h, and then I reciprocate the 1/3. 1/3, reciprocal of that is 3/1. So 3 times x is what I want to do. If I times something by 3, it's going to be larger. So horizontal stretch. What's the parent function? Absolute value of x. So I'm going to graph the parent function absolute value of x using 3 points of my choice. I'm not going to use the 5, 5 anymore, because if I times by 3, I'll be out of it, right? But I can use the 2, 2 versions. So 2, 2 symmetrically on the other side, -2 and 2. And then these two sets of points, these 2 points will be okay for this particular case. So 3 times x, vertex in the same position. Here we are at 2, 2 times 3 is 6. Make sure your y coordinates stay the same. And -2 times 3, you're at -6. You plot it, and there are your 3 points. For horizontal stretch, your graph has to be wider. Stretch horizontally, the graph has to be wider underneath the original graph. Same as before, the domain hasn't changed from the original graph. The domain is all of the real numbers and range y bigger and equal to 0. Okay, so we're gonna take a maybe 10-minute break now, or maybe yeah, right now. Take a 10-minute break. If you have a chance, you can go over some of these questions in your turn, 2.1 and 2.2, and then we'll continue on. So example 5, the point 8, -1 belongs to the graph of the function f. Find its image point on the function y equals f of. So you can see f of part. That means that's a b parameter, refers to the horizontal transformation. And then you want to always factor it out. For both of these questions, for both of f of 2x and this one, y equals f of 1/2 x, when you factor out that x, it won't affect anything else. But you always want to get into the habit, right? So you don't forget, because in this question here, that's going to matter. So let's tackle A and B first, and then we'll get to C later. This is 2 inside as a B parameter. That means we have a horizontal compression by a factor of 1/2. So we do the reciprocal of that number. We have to deal only with the points here. So the point 8 -1 becomes the point. The y coordinate doesn't change, it stays as -1 because we only are tackling the 1/2 times x. So we have to do 1/2 times the previous x, which is 8. 1/2 of 8 is 4. So 4, -1 is our point on the new function. Okay, the next one, find point on the new function f of 1/2 of x. Is it 1/3? I don't have my glasses. I think it's 1/2. So horizontal stretch, how do I know? Because in my mind, I already did the reciprocal of 1, 2. I flipped it upside down. So 2/1 makes it 2 times x. I already have the rule to which or the rule that I will use for changing this point into the new point. 8 -1 becomes 2 times 8. -1 doesn't change. 2 times 8 is 16, comma, -1. Always put these round brackets around points. Without the round brackets, it's just a list of numbers, no notation. So you make an annotation error when you leave the brackets out. Last one, find the image point on this new function. Now we're combining again all of the ones that we've seen so far. A bit selective here because I'm not including an a value different than -1, but I'm focusing on the new ones you have seen and how, if you don't factor this b value out, it will affect your c value. So let's start by doing that, factoring out the b value. 1/2 in front. X is going to come right after. We want to figure out what that number after the factoring will become. So here, I won't have +1 anymore because I factor 1/2 from this one as well, right? So what number times it will become 1, because that's what we want to get back. 1. Or 1 divided by 1/2 is what? This is the notation for the reciprocal as well. 1/1/2. That just refers to the reciprocal of 1/2. That's what we say. So if you have 1 over something, all it will do, it will reciprocate the number underneath. So 2/1. So in here, after factoring, you'll have +2. Now you can check your work. If you now multiply back to open up this bracket, so you do distribution, 1/2 times x, you're going to get your first term here, 1/2 of x. 1/2 times 2, you get 1. Okay, so then your factoring is correct. Everybody good with the factoring there? I'm going to take that as a yes. Now from left to right. This negative is the a coordinate, the a parameter that's going to be negative. So that one refers to a vertical reflection. So -y. So the graph will flip like this. So the signs of the y coordinates will change. Now here we have horizontal transformations. The b value refers to a horizontal stretch. Why stretch when the number is 1/2? Because the horizontal stretches and compressions need to be using the number in its reciprocal form. So not 1/2, but 2/1 times x. And then you see what happens to your x. It's a stretch. Now for this one, for the c parameter, That's our horizontal translation. 2 units, but where? This is opposite what the intuition tells us. To the left. So x minus 2 to the points. And lastly, we have a vertical translation, 3 units up. So y plus 3. Now, any point x, y, if I have to work only with points using these transformations, they become, let's see what point. For x's, we have 2x first, and then replace this one, and then subtract 2. So it becomes 2x minus 2, comma. For y, we take this negative y, and we plug it in there. So we have negative y plus 3. Now all we have to do is work with our point. The point 8, negative 1. So we have 2.
The 3.
Okay, you're good, Tom.
Lana, may I?
Yeah, go ahead.
Okay, so does not the negative y, the negative a, does that not affect the 3 and make it a negative 3?
No, not this one, no.
Okay,
If we would say, what would this function will become if we have a vertical reflection? So this is already the function, and now we want to reflect this function. Then this
Right.
becomes positive, and that becomes negative. But it's already the function itself. But now we want to know what the function f becomes based on all of exactly these transformations.
okay.
Okay. So let's plug in here 8, and this one is negative 1. So let's just calculate those points. So we have 16 minus 2, so 14. Positive 1 plus 3, so 4. 14, 4. Copying here for a bit. Maybe some of you are still copying. If you have any other questions, let me know. Okay, so we have done pretty much all transformations. This page has a nice little summary of all of the transformations we have talked about based on the standard form equation. Okay, so y equals a times f of b times bracket x minus c close to brackets plus d. Parameters a and d are belonging to vertical transformations. Parameters b and c are belonging to horizontal transformations. And you have a list of a summary here of all the transformations we have talked about. At the bottom of the page, you have a nice little formula. If you're having trouble converting these points questions into a formula for your points, you can always use this, this little equation to plug your A, B, C parameters into the formulas for your image points. Now, we haven't really insisted too much on the standard form because we haven't had all of the parameters, but now that we have them all, we can practice a little bit more with it. So in example 6, we're going to rewrite each of the following equations in standard form, and we're going to describe the transformations. So let's start with A. Y equals 3f bracket 2x plus 4 minus 2. So we're going to say y equal 3 times f of. Now here, remember, this is our b, always has to be factored out. So 2 bracket x. What's coming after x?
Plus 4.
Plus, not 4 anymore, because we factor out the 2 from the 4, but it is plus,
4.
not 4,
2.
2. Because 2 times 2 is 4. If you open up this bracket back to get to this form, you get your 4 back in this one, right? So 2 times x is 2x, 2 times 2 is 4. Clear for everyone how factoring and multiplication works? And on the outside here we have minus 2. You can leave it as minus 2 or write it as plus minus 2. Same like here in the standard form we have as x minus c. You can rewrite it this one as x minus minus 2. But I always found this one complicates things and confuses students, so I really insist on opposite. So read it opposite as is here, and this one just exactly as you see it. So let's see from left to right. This is the A parameter, that's your B parameter, that's your C, and that's your D parameter. So for A, if it's positive, we don't have a vertical reflection. If it's a number bigger than 1, we have a vertical stretch by a factor of whatever number you have there. This one is 3. The B parameter, if it's negative, you have a horizontal reflection. This one is not. If you have a number different than 1, you either have a horizontal stretch or compression. You always have to be careful with the horizontal direction because they act wacky. So it's not 2, it's going to be what number here for the multiplier?
1.
Not 1. Reciprocal of 2. So 1 over 2, okay? So you always want to reciprocate the number you see here. That's becoming a horizontal compression. Any questions about this? Okay, now we're going to see. The C talks about the horizontal translation. This one is also a little bit wacky because it doesn't go as you think it might go. It is 2 units, but it's going to go to the left. So x minus 2 is what's going to happen to your x coordinates. And lastly, we have our D parameter that's going to talk about the horizontal, the vertical, not horizontal, vertical translation, 2 units, where? -2, this follows exactly what you might think it would. 2 units down, y minus 2. So if I do ask you a question like this, to write a standard form and describe the transformation, that's all you have to do. Call it what it is, so name it, and then say what's going to happen to the coordinates of the points. Okay, let's go to B. Y minus 2 equals -4 f of -6x minus 3. So this one has a bit more. Now here is all right on the right-hand side. We have the A parameter times f of, here I do have to factor out this one in front of x. But then here I don't have a d value because the d value is moved over here. So we have to really add 2 to both sides to cancel the -2 from here and to move the +2 over here. That's the first step in writing the equation in standard form. Y equals -4 f of -6x minus 3, so +2. First step. Now the second step is what we always have to be careful with. Tackle this factoring. You cannot read the C parameter without the factoring piece. So f of -6 goes in front. X, and I'm gonna let you figure that one out. Let's see. First, you can figure out the sign when you factor a -6 out of these two. So we're focusing on -3 here, and then what's going to be here.
Is it +1/2?
Positive 1/2. Let's check. Negative times a positive is a negative. 6 times 1/2 is 3, correct. Okay, so we're having it all in standard form. Again, I don't care about these two signs particularly because I've taught you how to read them, okay? So let's go from left to right and describe each transformation. This is your A parameter. That's your A. That's your B. That's your C, but with the opposite sign, and that's your D with the same sign as you see it. So your A will give you two transformations here because you have a negative. So the negative itself tells you to do a vertical reflection, -y. The 4, it tells you that your graph will stretch. So vertical stretch by a factor of 4. So 4 times y. We're going now into the B parameter. The B parameter is -6. Again, the negative will tell you about a horizontal reflection, so -x. And the 6, it will tell you something about the horizontal compression or stretch. I'll let you decide that one. Now, we're never going to multiply directly by this number. So we need the reciprocal of that number here. So what's the reciprocal of 6?
1/6.
1/6.
Compression.
Compression, you got it. Now we're going into the C parameter. That's a horizontal translation or movement shift. 1.5 units. Now where, if it's positive here? Left or right?
Left.
Left. So x minus 1/2. And lastly, we also have a vertical translation, 2 units. This one is going to go up. So y plus 2. Did you get a chance to copy everything? You keeping up?
So it's a messy one.
Is it? So a lot of like HC, BC, BRs. Yeah, a lot of little, but you get used to it. I could have pushed a little bit more space on this one though. I agree with you. Left so much space for the last one. It is definitely easier for me to organize my writing because I know what's gonna be on the page ahead of time. Like you guys don't, so until you get used to the formatting. And you can also describe these transformations vertically. You just say A and then just write what it is. That's fine too. Okay, so last one, f of x equals 1/2 absolute value of negative x plus 3, close the absolute value sign, minus 1. So now here we have not f of g of, we have the actual function. If this bothers you, you can replace the actual function with the function notation. You can say, let g of x be the absolute value function. And then instead of writing the bars, you just replace it with g of notation. So for us, it will look like that. F of x equals 1/2. So no more bars, just g of negative x plus 3 minus 1. Because I know where these ones are in a function that's an absolute value function. So when you use this notation, don't put the bars again. Or when you use this notation, don't put the G there, because then it's a double notation, an error in notation. If you're choosing to work with this form, then you do exactly the same thing we've done here. Just keep using the bars. I'll show you maybe at the end. Okay, from left to right, we analyze to see if all of our parameters are in the right place in the standard form. So this would be your A parameter, that's your B right there, that's your C, that's your D. A and D, usually I don't care, but the B I always watch for, so always need to factor out. Even if it's just a negative, you still have to factor out. So let's rewrite it. F of x equals 1/2 G of negative bracket x minus 3 minus 1. Now you check your factoring. Negative times x is negative x. Negative times negative 3, positive 3. Yes. Your A parameter doesn't have a negative, so we only have a vertical compression by a factor of 1/2. B parameter is -1, so we don't have a stretch or a compression, but we have a horizontal reflection, so -1 times x. Horizontal translation for the C parameter, and we have 3 units where x what?
+3.
X plus 3, because it's 3 units to the,
Right.
you got it. And lastly, our -1 here is a D parameter. It's a vertical translation, 1 unit down, y minus 1. So the other notation will look like this. F of x equals 1/2 absolute value negative x minus 3 close. Oh, there's not two, only one, because we don't have the second bracket there. The second bracket is actually the absolute value now. Minus 1. That's it. So notice how I took off the g of, because I know what g of x is. It's absolute value of x. So I just put the absolute value sign around it. And then here are your horizontal transformation. Here are your vertical ones. So outside, inside. Outside vertical, inside horizontal. Everybody good? And there's some work again with in your 22.3, a similar work, because I really want you to get in the habits to write your equation in standard form. And then we're going into some graphs now using all transformations. There's definitely going to be questions in your test, and you have to show your work. Each graph in part, the same way we have done in some other parts of our notes. But also you can do transformations with graphing where you can do image points only. And in this question, in example 7, I will show you the image points only approach. So sketch the graph of the following function using image points, so not each graph separately. State the domain and the range of your final graph. The work until we get to the points for each of the transformation is going to be the same. We're going to make sure we identify the type of parent function we're going to work with. For this one is the square root of, and notice how far this line goes, because that's where it stops, right? The inside of the function stops right after +2. And then we're going to make sure our standard form equation is written correctly so we can read the transformations correctly from it. That's why it's called the standard form equation, because it's the standard from which we take our transformations from. So y equal 2 times square root of, now we see how we have a negative 1/3 in front of x. We want to factor that one. So negative 1/3 bracket x, and then we have to figure out what comes after it when we factor out the negative 1/3 from 2. And at the end of it, we have to have -1. This is outside of the square rooting. So let's see what we get. You can also think about it backwards. 1/3 times what gives you back your 2?
One.
With 1 here, 1 times 1/3 is going to give you 1/3 here. So you need more than that. The question is, what number? I'm even going to ignore the signs. The sign we're going to figure out later. But what number times what will have to equal this 2 here? Because basically, when you factor out the 1/3, you're saying it's a factor of 2. So what's the other factor?
8.
Well, if you do 8, let's try it. Okay, these are all great trials, everyone. Okay, thank you for your answers. So 8. Now let's check. 1/3 times 8. Can I cancel 3 with 8 to get 2? I'll get 8 over 3, which is a bit more than 2. Not exactly 2. So not 8. You're a bit too high now. So 1 was too low because we still got only 1/3. 8 is too high.
6 then.
6 right here. So now you check it, right? 1/3 times 6. I can cancel 3 with 6, 1, and 2. So I get that 2 back, right? So here you have to have 6. Now let's figure out the sign, right? I have to get back a positive. So negative times what sign would be positive? Negative or positive?
Negative.
Negative. Okay, so like that, very easily just think about it backwards, but in the end, you can also think about it as division. 2 divided by 1/3. That's what you're doing in your mind. 2 divided by 1/3, because the 1/3 was the factor. So if you do that, you find the other factor of 2. Well, this is the division of fractions. So 2 over 1 stays times the reciprocal of 1/3. Here's a reciprocal again. And then you just multiply. 2 times 3 is 6 over 1. So 6. That's like, oh, right. Division of fractions always gives people the hives. Okay. So we have our factoring form. It's called the standard form. So we're going to go from left to right and describe the transformation. I'm going to color code my vertical transformations from my horizontal transformation. So here I have the A parameter that gives me a vertical stretch by a factor of 2. I'm skipping to the end of it. That's a vertical translation for the D parameter, 1 unit down, or Y minus 1. Here's our B parameter. It has 2 parts, a negative and the number itself. So we have to treat it separately, especially when you have to do the graphs separately. So negative, it gives you a horizontal reflection, so negative x. The 1/3 gives you a stretch or a compression. Let's see which one is it. Let's reciprocate the 1/3 to what? 1 over 3. 1 over 3, let's reciprocate it. Becomes what? 3 over 1, or 3. So 3. Is it a stretch or a compression based on this multiplication?
Stretch.
Stretch. And then we go to the C parameter. Horizontal translation, 6 units to the right. So x plus 6. Okay, so this is how the table works, because it's a little bit of a different table. It's not a table of values. It's a table for keeping track of the points. So here in the first column, I'm going to put the xy that belongs to the function square root of x on the parent function. And this xy becomes the following xy with transformations. So here's our x's. So negative x, negative 3 times x, negative 3x plus 6. So negative 3x plus 6. Comma, and then we'll move to the vertical transformations. 2 times y minus 1. So our parent function, we said it's square root of x. We know the points for the swoosh graph. We already worked with it extensively today. 0, 0. And then it's 1, 1. And then it's 4, 2. Let's skip the graph and then sketch the swoosh as well. 0, 0, 1, 1, 4, 2. And now we're gonna have to do some calculations here. So this is our x's. You gotta make sure you stay focused on your x's for the first column. So 0 plus 6 is 6. We'll go to the next x. Negative 3 times 1 is negative 3 plus 6 is 3. Negative 3 times 4, that's negative 12 plus 6 is negative 6. So all the x's are done. Now we're going into the y's. For the y coordinates calculations. 2 times 0 is 0 minus 1 is negative 1. 1 from here, 2 times 1 is 2, minus 1 is 1. 2 from here, 2 times 2, 4, minus 1 is 3. So our points are 6, negative 1, 3, 1, negative 6, 3. We go to our Cartesian plane, 6, negative 1. Three, 1. And negative 6, 3. And that is the graph of y equals 2 square root of 1 over 3x plus 2 minus 1. You can see the horizontal reflection, how the graph did reflect horizontally. You can see the vertical stretch by a factor of 2 because the distance between these 2 points is now 1 anymore. See here was 1, now it's 2. Which one is the other one? We also have a horizontal stretch by a factor of 3. You can see the graph is stretched. We can see the downward movements by 1. And we can see the movement to the right, 6 as well. Now for this one, the domain changed and the range changed as well. So let's see. The domain changed because we had a horizontal reflection and the movement to the right. So both of those things affected the domain of the function. So we have a starting value of x at 6, and then everything is less than that value. So x is less than and equal to 6 from all of the real numbers, of course. I think here I moved this one. It's supposed to be 3, but I put it at 2. I'm gonna redo this part here. I hope you guys did it at 3. Because I remember saying 3, but I put it at 2. There you go. And then for the range, we have y. Now we didn't have a reflection for the range to change it into the opposite direction, but we did have a movement of the graph downwards by 1. So the range doesn't start at 0 anymore, and upwards it started at -1 and up from there. So all the values of y's are larger and equal to -1. I have 2 more pages to do, and then I'll let you work on the partial. This is a simple question, the second last one, how to write equations from descriptions. So the graph of f of x is reflected over the y-axis, the first one, and then undergoes a vertical stretch by a factor of 4, a horizontal compression by a factor of 1/3, a vertical translation 5 units down, and a horizontal translation 3 units to the right. Write an equation for the new function. Since you're writing an equation for your new function, your equation from these descriptions have to be in standard form. A times f of b times x minus c plus d. So what I need from all these descriptions is to translate it into an A parameter, into a B parameter, into a C parameter, and to a D parameter. So let's go one by one. Reflected over the y-axis. So here's your y-axis. Here's the reflection direction over the y-axis. What kind of reflection is this? Horizontal reflection. Horizontal reflections tells you that your B parameter is negative. So B is less than 0. The first description here we tackled. Undergoes a vertical stretch by a factor of 4. So vertical stretch 4 times y. We know that this 4 right here, it's going to be in the A parameter. But we don't know yet if we have a vertical reflection yet. So we're just going to say just the number itself, the absolute value of A is 4. Not complete unless we finish the analysis of the question. And it's direct. Whatever you see here, that's your A. And then we have a horizontal compression by a factor of 1/3. So horizontal compression by a factor of 1/3 times x. Now this one, you gotta pay attention, right? Attention. That when you put it into the equation of your transformations, b and the factor is not the same. Here, a and the factor by which we apply the transformation is the same. But here they're not the same. What's the relationship between them? They are reciprocals of one another. So if this is the factor, the b value was going to be the reciprocal of the factor, which is 3/1 or 3. This one also in absolute value at this step, because I'm not talking about the reflection in this step. It's not a big detail. I wouldn't take any marks off, so don't worry, but you got to remember the B has 2 parts, 2 transformations, the reflection and the stretch or compression. We do have both information for the B values, so if we're putting these 2 together, we know what B equals to now. We know it's negative, so negative, and we know the number, 3. So we know B. A, we might know 2, unless we found a reflection in the vertical direction as well. Okay, the next one. Vertical translation 5 units down. Vertical translation 5 units down. This one is in which parameter from the equation? The vertical translation. A, B, C, or D?
Is D.
D. And D is
-5.
-5. This one also is known directly by the movement downwards, so D is known directly. The last one, horizontal translation, 3 units to the right. Horizontal translation, 3 to the right. C parameter. Now, to the right, C means is +3, but you gotta be paying attention when you're plugging it in, okay? Because yes, it is +3, just like you see it here, but when we put it into the equation, it has to be with an opposite sign. So let's write it down, opposite sign in the equation. C is known, D is known, B is known. A, since we didn't have found a vertical stretch as well, we also can conclude that A is just 4, +4. So once you have A, B, C, and D, you can just plug into your standard form to begin with. So Y equal blank F of blank X blank, 2 brackets, and then blank. So let's see. A is 4, so I would just put 4 right there. B, we said is -3. This is where C is, and we said we make sure that it's opposite sign in the equation. So it's gonna go as X -3. And D goes just as is, so -5. Or +/-5 if you want, but it's not a big deal because you only need a standard equation for transformation. To answer a question like this, you want to get rid of all these brackets. You don't need them. Y equals 4F, and here we can just multiply through -3X plus 9, close the bracket, -5. So that's the equation in the simplest form we can write it, but we needed to go to the standard form to get to it. Now, if I would know what type of function f is, I may be able to get rid of even more brackets, but since I don't, it has to stay in this form. Okay, so let's take a 5-minute break before this question because I need your energy. Maybe you want to grab a refill on your coffee, just like I will be doing. So it's 3:24, so 3:30 is when we're gonna start this. Okay, so let's tackle this last question. Now, this question is sometimes difficult for students because it can have various levels of difficulty. So if you're asked to go from an image of a transformation that happened to an original graph and then deduct from those 2 graphs what kind of transformations were applied. So it's a type of a backwards question, but this type that we have learned about stretches and compressions and reflections and all that, we actually have to factor those ones into the equation. These questions, yes, can get quite difficult. And a lot of the times we can figure them out just by looking at the graphs. So I'll show you that method from example 9, because we can definitely do the entire example 9 just graphically, the graphical approach. But sometimes it is not sufficient. And we found out this one the hard way, when sometimes it doesn't work and you have to look at points and start plugging in. So I will show you today how to check your work algebraically using the equation for image points. So let's first read this question. The graph of g of x, so this graph here, the graph of g of x is the image of the graph of f of x. So this is the graph that we got from the original graph after some transformations. So after combinations of transformations. Corresponding points are labeled, and you definitely need corresponding points to ease your deduction. So here we have this point is going to be corresponding with that point, so the origin point, and then we have the next point, P, it's going to be corresponding with P prime. What is the equation, or what is an equation of the image graph? So the equation for g of x in terms of the function f of x. So we want to know how we got from f of x to g of x. So basically, g of x equals something f of something x something, and then d at the end, right? So the graph of f is being transformed after a series of transformations. All we have to know is what's happening with our graphs to figure out the variables a, b, c, and d. Now, I gave you at the bottom a method, and the first step would be identify reflections, and the second step would be identify translations. Either or, it doesn't really matter, like you have to figure them out, but just these ones seem to be the easiest ones to spot when you use the graphical approach. So for the reflection, if I look at this graph, immediately I can see that for the horizontal direction, my graph has the same swoosh, right? So here I swoosh to the right, here I still swoosh to the right. So the horizontal reflections, I can conclude there are none, right? But how about vertical reflection? This is the graph, and now it's going sort of upwards above the x-axis. Our second graph, the image one, goes underneath the x-axis in that direction. So this one, yes, it happens. Now, when you have no reflection in the horizontal direction, that's going to happen here in the b parameter. So we know the b parameter will be positive. When you have a vertical reflection, that's going to happen in the a parameter. We know that the a parameter will be less than 0. So far, so good? So you look at your graphs and see or identify if there are some reflections. And then, because we are working towards an equation, we want to go to the parameters with that pieces, those pieces of information. Okay, so the next thing is identify translations, but this one can only happen if you have some nice points to work with. If you have a point where either your x or your y coordinate is 0, those points or both of them can be 0. For our example, we have one that has both zeros, the origin. Then you can identify really easily translation, because those types of points won't be affected by stretches and compression. So you can clearly see if the graph has moved left, right, up, and down. With the other points, you don't know exactly if where you see it is actually from a movement down or left, right, because maybe the stretches also move the point in a similar fashion. So you can't conclude for sure. That's why the point is there. So any point of the form, for example, 0, y. Does this one say x here? Yeah, right. So let's put that y there, 0, y, because I have a typo there. So if you have a point of the form 0, y, so basically our x coordinate is 0, y can be whatever it wants, okay? So it can be anywhere on the y-axis, okay, the original point. Then this point, clearly, it will show you a horizontal translation by whatever number you're gonna have in your new point, okay? So since our point is 0, 0, the original one, and it moved to the point -4, -3, okay, I can see my horizontal translation right here in the change that happened in that x coordinate. So horizontal translation was 4 units to the left, which tells me my C parameter is -4. If you have a point similarly with whatever x you want, but then a 0 for your y coordinate, this is going to be really easy to detect vertical translation, because this being 0, if you times it by a negative or by a number different than 1, it won't change the translation part of your graph. You can clearly see what the translation is. You're going to use the same point because that point follows this rule as well. So we have a 0 for the y coordinate for our origin point, the same point that goes to -4, 3. But this time, this is the translation, 3 units up. It's -3, right? So down.
I have a question.
Yeah.
About C being -4, doesn't
Yeah.
the sign reverse?
Sorry.
Doesn't the sign reverse?
Well, because we're not reading it backwards, so we're not going from here, oh, we're gonna go up, you know, we're actually reading it from here down.
Yeah.
Yeah, so it's gonna be negative. Because to go from this graph to that graph, we're gonna go 3 units down and 4 units to the left.
Okay.
When we're gonna put it in here, we're gonna go with plus, because we have to read it as -4.
Right. Okay.
Right, okay. Okay, so -3 here, everyone, okay, because I put from this point, I put +3, but it's -3. So vertical translation 3 units down, which makes our D parameter -3. So far, what do we have? We have a C for sure. We have a D for sure. These ones we only know one it's still staying positive and one it's negative, but we don't know their values yet. Okay, so now we're going into stretches and compressions. That one I need a bit more space. So let's go divide it into 2 and leave some space here to do your equation at the very end. So number 3 step is do your best to identify stretches and compressions. So let's go for the vertical direction first, vertical stretch / compression. For these ones, we need to look at our graphs and identify distances in the vertical direction between the points we are using. And we only need 2 points, 2 consecutive points in our graphs, the ones that we are using. So let's call the distance between the origin and the point P our D distance. So D for distance. And then we're going to look at the image graph between our 2 points because we're doing vertical stretch / compression. We don't know yet. Let's call this distance D prime. Now, when you're looking, just simple comparison, did our graph compress or stretched vertically from this one to that one?
It's stretched.
Well, if you look at from this to that, yes, but you have to look at the f of x towards g of x. So this is your original graph. This is your new graph. Did it stretch, become like steeper, or did it become narrower, compressed vertically? So this is a vertical stretch. This is a vertical compression. So if it's not white, it's black, right? So it's a vertical compression by a factor of 1/2. You can see the distance is half the distance it used to be. Now, a lot of the times it's easy to figure out the factor 2 just by looking at the graph, but sometimes it's not. So here's a little formula you can use to figure out your A parameter. So if you take your A parameter and you times it by D, you should get your D prime. Right? So now we know what D is. We can count it 1, 2 from there. So A times 2 equals, we know what the D prime distance is, 1 square length there, 1. All we have to do is figure out this equation to solve for A. A is, divide both sides by 2, we get to 1/2. Now, A from here, and with the information from here, this is A negative, we can also conclude that A is going to be negative 1/2 in the final equation. So far, we have A is complete, we have C is complete, and D is complete. All we have left to do is figure out B parameter. We know it's not negative, but we don't know if it actually is a number or not, different than 1. So let's tackle horizontal stretch / compression and figure out what it is. It's a similar approach. I'm going to use, I guess, blue for the distances. So we need, again, a distance, the horizontal distance between 2 points. So here we have the original horizontal distance between our points, 1, 2, 3, 4 of them. And then here we have our new horizontal distance, D prime, between the 2 points. Now the formula is similar with the way we treat the B value when we read it from the equation. We say B times the reciprocal of D, or the other way around. We can do the reciprocal of B because it's going to be easier for you to remember the formula, but it's going to be the same thing. We can say the reciprocal of B times D equals D prime. And now let's replace D and D prime with the distances that we see from the graph. We have 1 over B times, this D is 1, 2, 3, 4, equals, and this D prime is 1, 2, 3, 4, 5, 6. Okay, now before we calculate what the B is, because we will based on this equation, let's see if we can figure out if it's a horizontal compression or a stretch. So this is the distance, and now this is the new distance. Did the graph stretch or compress?
Stretch.
Stretch. So this is gonna be a horizontal stretch. Okay, so let's find the horizontal stretch. Our B value has to be less than, okay, between 0 and 1 for the B itself. So let's see, 1 over B, we're gonna divide both sides by 4, or we can do 4 over B equals 6, and then we can just cross multiply at this level. So you just can solve this however you want, as long as you don't break any algebraic rules. So I always like to make my equations that have fractions into what we call a proportion. So a fraction equals another fraction, and then I can just cross multiply. I will end up with 6b equals 4 times 1. And then divide both sides by 6 by the coefficient of b. So b is 4 over 6 or 2 over 3. And this is the actual b, because we already know it's bigger than 0. So it's not going to change its sign. So it'll stay as 2 over 3. Okay, so I recopied the setup from the beginning of this question with all of the blanks for the parameters A, B, C, and D. All we have to do now is plug in and then get rid of some brackets if we have extra brackets. The first step, plugging in, always the same. Start with A, negative 1/2 there. B, 2/3. Now for C, attention, opposite sign in the equation, okay? So you're not gonna write x minus 4, you're gonna write x plus 4, so you can read it as negative 4 when you do the transformation. And D just as it is, minus 3. All good, except for these extra brackets. The factoring is only needed for the standard form, so we can read the parameters for transformation purposes. For equation writing purposes, we don't need all these extra brackets, so it's nicer if we don't have too many of them. So we're gonna just open that up and simplify the look of our equation. So g of x equals negative 1/2 stays in front, f of 2 over 3 x plus 2 times 4 is 8 over 3, close bracket, and then minus 3 stays by itself. And that's our final answer. So how do you feel about this question?
It's gonna take some practice.
Yep. It will definitely take a little bit of practice, this one. I have an extra, I think a couple of extra ones that I can provide you with if you want more. But I also want to show you like a different approach before I let you go for partials. Everybody ready? So you can grab a piece of paper if you want, that you don't use, like a scrap piece of paper, anything. We're still gonna work on the same question. And I'm gonna tell you how to use points to deduct all of these values, the A and the B and the C and the D. So I think it might be easier for some of you to use the image points equation. So this one is found on page 30. Okay, so on page 30 at the bottom, you have the image point equation. For any point on the original function x, y, you get a new point called the image point that is called 1 over b times x plus c, comma, a times y plus d. So all your new points follow this rule, right? So you would have reciprocal of b times x plus c, and you have a directly times y plus d, okay? Now, since we know original points and new points, okay, we will be able to figure out the parameter using some series of equations. So let's do a little table. I think maybe table would work nicely. Here's my little leader. So we're gonna do a table with our points that we have and our new points. It will have 3 columns. Okay. So let's start with the first point, the point 0, 0. Okay, it will become the point -4. I'm going to put it over here, -4 and -3. Everybody agrees with that? The point 0, 0 becomes the point -4, -3. Clear? Yes, right? Okay. Now, using this equation, let's write a formula, if you want, by plugging in the 0 in the equation. So I would have 1 over b times 0 plus c. Okay, and for the other one, I would have a times the y from here, 0 plus d. That would have to equal this new point because they are all related, right? Now, what do I get from here? 0 times anything is 0, right? So I'm left with c, and c will have to equal what? -4. Done. I found my c. How about the d? Let's see. A times 0 is 0 plus d, and it will have to equal this one, which is -3. Found. So C and D found from the first point selection. And that's what we've done for our graphical approach as well. So that's the first one. Now for the other one, we're going to be using the other point. So the original point 4, 2 must become the point 2, -4. Okay. We're going to plug in the 4 as an x and the 2 as a y into the formulas here. But we also know what C is. C is -4 and D is -3. So let's see what happens. We have 1 over b times x, which is 4, plus c, which is -4. That's the first one. And then for the second part, the y coordinates, we have a times 2, and d is -3, so plus -3. Those are our rules. Now let's take them one by one. Right here, this part has to equal the x on this part. So we have 1 over b times 4 minus 4 equals 2. This one I don't know directly what they are, so I have to calculate it. So let's calculate it. 4 over b minus 4 equals 2. Let's move this negative 4 on the other side. 4 over b equals 6. 6 over 1. You can cross multiply. We end up with 6b equals 4. Divide both sides by 6. b equals 4 over 6 or 2 over 3. We got our b value. And then we have this part here equals that part there. So this transformation on y has to equal that y value. So let's see what we get there. So we have a times 2 or 2a plus minus 3. So minus 3 equals negative 4. 2a, move the negative 3 on the other side, becomes positive 3, or add 3 to both sides, you get negative 1. Now divide by 2 both sides. A is negative 1/2. Is that what we got with the other approach? Yes. So you have A, you have B, you have C, you have D. So anytime you're using the graphical approach and you're stuck, remember this, okay? So plug in into your equation, whatever you have, and then compare to what you should be getting into your new points. And you can still solve it, but algebraically. These are basically solving a system of equation, but I split it up into 2 parts, so it's a little bit easier to digest. Which one is easier?
Personally, I think it's the first one, but
Okay. Let me know if I have to move it a little bit back to the first part. But yes, I like the first one too. I think that was Luke, right? And for years, I've been teaching only that method. But unfortunately, sometimes with the more difficult questions, you're kind of stuck with that method. So you need to be able to compare the points. And it doesn't necessarily, it's not translating into a method per se, like all of your notes are telling you, you can use the points too to check, because the relationship always happens. But without an example in the notes, a lot of the time students are a bit stuck. So my decision is to introduce you to the method. So in case you need it, you have it in your examples as well.